Welcome back to the third and final installment of the Multidimensional Diffusion MRI lecture series. In this third part, we'll discuss potential applications. I think it's always exciting to have a new form of MRI contrast to work with. It's not necessarily obvious where it will have the most impact, but I'll mention a few ideas and review some recent publications. The first potential application is to probe gray matter microstructure, which is much less coherent than white matter and therefore might particularly benefit from this type of encoding, which is able to get at some of the information about the subvoxel compartments even when they're not coherently organized. The second is improved sensitivity to changes in axonal structure. So now that we can generate these microscopic fractional anisotropy maps, where the pathology is not obscured by axonal dispersion effects, there could be some big benefits. And lastly is microstructure-informed tractography. The information about the subvoxel compartment sizes and shapes may provide additional information that helps improve the robustness of tractography. Before we review some of the literature, I just want to say a few more words about probing gray matter. I really think this is the next frontier for diffusion microstructure imaging. And one key element is the need for sufficiently high spatial resolution to ensure access to really pure gray matter signals. The high anisotropy of the white matter can so easily dominate for even relatively small partial volumes. So I think we might only see the real potential once we combine the multidimensional diffusion encoding with more advanced image acquisition, image encoding, image recon schemes. Okay, so turning now to applications of multidimensional diffusion encoding in patients. I'll start with an example from my lab where we took this 5-minute clinical protocol and looked at some multiple sclerosis patients. And here we show an example where there are some lesions that happen to fall in a crossing fiber region. And you can see they're obscured in the fractional anisotropy map, but much more clearly identified in the microscopic fractional anisotropy map. We also found some unique types of contrast within the larger lesions that didn't correlate with any of the other contrasts that we saw in the structural images or other diffusion images. This is an example looking at traumatic brain injury. So here they use double diffusion encoding to estimate the axon diameters within the optic tract. And they found a difference in the right optic tract of the injured rat brain. And then did a very nice comparison with a neurofilament stain, which also substantiated the change in microstructure in that region. This is a really nice paper from Tim Derby's group. They also looked at multiple sclerosis patients, and they showed that the microscopic fractional anisotropy did a better job of distinguishing between the healthy controls in two different patient populations, and also that the microscopic fractional anisotropy values themselves were more tightly correlated with disease symptoms. And they also demonstrate ways in which the different sensitivities to the microstructure could really matter in some of these cases of pathology. This is a beautiful study from Marcus Nielsen's group where they looked at epilepsy patients and a number of different types of lesions. This is an example of a focal cortical dysplasia, which is a neurodevelopment abnormality. And you can see that their microscopic anisotropy map picks up a hyperintensity that isn't seen on the FA map. And it's a really nice indication of the ability to pick up some of that more subtle microstructure. This is another example from my lab where we looked at some of the multidimensional diffusion encoding measures in a healthy aging population. And here we're looking at some mean diffusivity measures using conventional DTI versus the multidimensional diffusion encoding, and show a much wider range of values for the multidimensional diffusion encoding, or the QTI derived metric, and the correlation with a delayed recall or a memory score in those volunteers. So this inspires confidence that this type of encoding may provide improved sensitivity to microstructural correlates of behavior or disease. And this is a paper on white matter degeneration, also an aging study, and also in Parkinson's patients. And they compared a whole variety of metrics and showed some quite clear correlations with age that included the microscopic fractional anisotropy. And then this is another paper from Marcus Nielsen's group where they looked at tumors and showed actually a drop in microscopic anisotropy where there was an increase in mean diffusivity for classic DTI, but a drop in microscopic anisotropy in some of these tumor regions, which is also another unique type of contrast for this type of pathology that could add to the overall information in an assessment. So in summary, multidimensional diffusion encoding offers new form of contrast and novel microstructural information. Potential applications include probing gray matter microstructure, improved sensitivity to changes in white matter microstructure, and tractography guidance. Initial demonstrations of multidimensional diffusion coding in patients includes multiple sclerosis, traumatic brain injury, epilepsy, aging, Parkinson's, and cancer. So I think this is an exciting new area where there's a lot of active research going on, and that is the conclusion of this lecture series. Thank you again for inviting me to be a part of the workshop this year.